Okay, well, we're going to have our class now. This is Strength of Materials. It's Thursday. I wonder if I need to adjust anything here. It's not too bad. Looks pretty good. Okay, well, let's see who's checking in here. We've got Alex, Ashley, and Ben Seaman so far. And it's time for class. So we're going to get started. Do any of you have a comment or question before we begin? Well, okay, I don't hear anything. We just have the four of us right now. Let's see where we are in our course here. This is the 5th of November. And homework number 24 is due, I guess, Sunday night. Yeah. Homework number 24 is due Sunday night. It's chapter 6, problem 171. Due Sunday. And we start next week on chapter 7, which is all about shear stress when you have bending. See, when you have bending, you know you get normal stress, and you have an equation for it that is called the Flexure formula. And we'll be doing that today. This is our last day on chapter 6. And see, next week, we're going to be in chapter 7. See, this is chapter 6. Next week will be chapter 7. But it turns out that when you have a beam that is bending, it's got a bending load, you have shear stress. Not only do you have normal stress, but you have shear stress also. So I'll just talk to you about that for a minute, and then we're just going to work problems. We're just going to work problems today. Now, talking about bending, if you had a nice, simple rectangular beam, there's a rectangular beam under a typical bending load, you would have compression on the top and tension on the bottom. And the distribution looks kind of like this. And you get the maximum normal stress at the top, and you get the maximum normal stress at the bottom, as you can see. And right here they have a name for this. It's called the neutral axis. There is no stress there at the neutral axis. It's not tension and it's not compression. There's just no stress, there's no strain. But it turns out, if you have a bending load on the same kind of rectangular shape, you get a shear stress distribution that kind of looks like this. You have your maximum, shear stress right there at the center, and you have the shear stress at the bottom, and the shear stress at the top is zero. It's just the opposite from the normal stress. And I'll try to show you something else here in your book. Just giving you a tiny introduction to where we're headed. In your book, on page 377, is a picture of a beam. It looks like maybe a 4x10 wooden beam, and it has a crack. There's a crack all the way down the center of it. Those of you that have your book and you can turn to that, you'll see that crack. You know what's causing that crack? Well, it's not normal stress, it's shear stress. The maximum shear stress occurs at the neutral axis. They probably shouldn't have named it neutral axis, because that's where it is on normal stress, but here, that's where you have your maximum shear stress. And wood fibers run along the length of the axis of your beam, and they can slide on one another, and they slid on one another, and it cracked that beam right down the middle. You'll see it there on page 377. Interesting. And we'll learn this equation here. This equation is called the shear formula, and we'll learn it Tuesday, but not today. Today we're still in chapter 6, and I want to make sure you understand chapter 6. But the way this one goes is and you already understand some of these things. You know what that V stands for. That stands for your shear force. We've made shear loading diagrams before, and that's where, in fact, that's where you get that shear force. You get it from this shear loading diagram. And you see this bending moment here? Guess where you get that? You get that from your bending moment loading diagram. That's where you get those. This Q will explain, or you could read about it. We'll explain it next week. The T refers to the thickness. That's down here. That's how thick your beam is. This I, well, you know what that is. That's the same I as this here. It's called the area moment of inertia. And we know how to figure that, and we'll do some of that here in a minute. Really, the only thing you don't know about the shear formula is what this Q thing is, and I'll explain that next week. But right now, that's enough of an introduction to where we're headed. Let me see when the next test is too. I think that's next week. Let me look it up here. Let's see. You're going to have a test, and it is, well, let me keep looking here. I think I've got my pages all mixed up here. Look here now, let's see. Yeah. Your test is November 17th is when it's available. When is that? Well, today's the 5th. Right? Oh, that's a long time from now. Never mind. That's a week from Tuesday. Your test is the 17th. I could write it down though. It wouldn't hurt anything. Your exam 3 is November 17th. It's a Tuesday. And it's over chapter 6 and 7. Well, we haven't even started 7 yet. But 6 and 7 are pretty long, difficult chapters. And we're still in 6 right now. But that's where we're headed. There's some homework for you. I gave you some info about where we're headed. Do you have any questions, anybody? Any questions or comments? Okay. I'm going to erase all this and we're going to do a problem. We're going to do problem 688 together. That'd be good. All right, I'm going to erase all this. Here goes. Yeah, there we go. Now let me see if anybody else has showed up here today. Oh yeah, look at here. We have Braxton, Ben Seaman, Alex is here, Samuel, Shane, Mohammed, Jackson, Brian. We've got a wonderful class. All right. Good deal. Okay, we're going to do problem 688. Now let me find it. Some of this is sort of review. I want to make sure you understand chapter 6, because the next test will be over 6 and 7, right? Yeah. Okay, I found it. All right. Well, now you're supposed to make these free body diagrams to scale. I guess I could try to make mine to scale. It wouldn't hurt a thing. All right, so here we go. We're going to try to make this free body diagram to scale. And 6, 3, and 6, huh? Well, okay. Maybe. Now, it looks like you've got a pin here, a smooth pin right here. Smooth pin. And a distributed load right here of 2 kips per foot. Now, is that showing up on our picture there? Yeah, pretty good. And then you have and then you've got a 12 kip. See, this is 9 feet. And then this is 3 and 6. This is about like that. That should be red though. And you've got a roller here. And a fixed connection here. Okay, how did I do? Looks pretty well. This is A, B, and C. We could label that A, B, and C. There's my free body diagram. I need some red stuff. Let me put some red stuff on here. You know you're going to have a force going up here. We could call it the force at C. That's a good name for it. And then this is, they said this is 12. This is 12 kips. 12 kips. There we go. That'd show up pretty good. Maybe. And then, hey, look at here. You're probably going to have a force going up here at A. Why don't we call that FA? That's a nice name for it. And can you see that this fixed connection could provide a couple? Absolutely. And why don't we call that couple MA? That's a nice name for it. We'll call it MA. There we go. That's pretty good. Now this distributed load has a resultant equal to its area. We learned that. We memorized that the resultant of a distributed load is the area. Well, it's a rectangle. It's 9 foot times 2 kips per foot. I can do that. The area of our distributed load is 9 feet for the base. We'll write it out. 9 feet times 2 kips per foot. Well, I get 18 kips. See, the feet cancel. And so you get 18 kilopounds. Well, that's what that is. This here is 18 kilopounds. 18 kips. There we go. Well, there's all the red stuff. And then what we're going to do is the shear loading diagram. And then the bending loading diagram. Now, what do they want us to do? Let me read it. This is problem 688. It's on page 308. It's on page 308. They want the absolute maximum bending stress in the beam. See, in the next chapter, we'll be able to figure the absolute shear stress in the beam, but we don't know how to do that yet. Each segment has a rectangular cross section with a base of blah, blah, and a height of blah, blah. Well, let's draw that. Let's draw that. You don't need this anymore. We found the resultant of that distributed load. But what we're talking about here, see, this is the cross section. There it is. Yeah, it's kind of hard for me to draw, but you get the picture. What we're looking at here, we'll make a bigger one so you can see it. It's 4 by 12. It's 4 by 12. Puts you about like that, doesn't it? Did I do good? 4 inches. 4. Yeah, that's about right. 4 by 12. That's what this cross section looks like. I think I made mine a little too thick there, but you get the picture. There you go. Oh, well. While we're at it, let's get the moment of inertia of a 4 by 12. Well, you know what the formula is. It's 1/12 base height cubed. So I can do that. You do it too. Make sure I get this right. Here we go. 1/12 1/12 4 times 12 cubed. Did you get 576 cubic inches? No, wait a minute. No, that's wrong. Inches to the fourth. There. Inches to the fourth. Okay, we got that. Now what? Well, now what we're going to do is the shear loading diagram. Well, no, wait a minute. Wait a minute. Before we can do a shear loading diagram, we got to clean up some of these unknowns. Now we have 3 unknowns here. We have this moment provided by the fixed connection. We have a force going up at A, also provided by the fixed connection. And we have a force caused by the roller at C going up. We've got this 18 kips here and this 12 kips here, but we have 3 unknowns. What I'm going to do is I'm going to let you work on this for a couple of minutes. I want to see if you can figure it out. See if you can find this bending moment at A and that upward force at A and that roller force at C. I will shut up and I'm going to let you work for a couple of minutes. I think you'll learn more struggling with that than just watching me do it and being bored out of your gourd. Go for it. I'll give you more than 2 minutes, maybe 3 minutes. Work on it. I'll be back and we'll do it together. Well, I don't know if I'm back now. I gave you guys a little time to work on that. I don't know if I gave you enough time. Anybody think they've got any of those unknowns there? Just go ahead and speak up. I'm listening.
Yeah, I think I got him.
Yeah, go ahead. Who am I talking to?
Shane.
Shane. Tell me what you think, Shane.
I think the moment at A is 117 kips. And
Now,
force at
Shane,
C.
wait a minute, Shane. Moments aren't measured in kips. Let me tell you, force is measured in kips, but moment is not measured in kips. Moment is measured in, well, several things. I mean, you could measure it in kip feet, but you don't measure moments in kip. Go ahead. Sorry to interrupt, but I want you to learn that. That's really important. Go ahead, Shane. I'm still listening.
Gotcha. And the force at A is 24 kips. And force at C is 6 kips.
Well, I hate to tell you this, Shane, but you are truly blessed, Shane, because those are all wrong, and you're going to learn. Now, see, if you got those all right, then what I'm going to teach you here wouldn't help you because you already understood.
Gotcha.
You don't understand, or else you just made a mistake like we all do. But those are all wrong. But I want everybody to know that moments aren't measured in kips, they're measured in kip feet. Okay, well, let's, anybody else? But I appreciate you trying there, Shane. Good for you. Proud of you. Anybody else want to have a go at what they think those unknowns are? After I was so rude and unkind to Shane, nobody wants to speak up?
I'll take a try at it.
Yeah, go for it. Yeah, now who am I talking to?
This is Braxton.
Braxton, go for it, Braxton.
I got FC as 4 kips, FA at 26 kips, MA at 153 kip feet.
Braxton, you didn't learn anything.
Oh.
No, you got him right. Braxton, you got him right.
Oh, okay.
You got him right, but see, you didn't learn anything because you already knew how to do it. Now good going, Braxton, proud of you. But let me go ahead and show the others how to do this, because there might be some other people that need a little help. But Braxton, since you got that right, how did you do it? Tell us what you did.
You couldn't just solve it with one force equation and one moment equation. So you had the section. I took the section from B to C and did a moment equation for that.
Absolutely right. That's what I was going to tell the students. What you first do is you try to do the sum of the forces on the whole free body diagram, but it doesn't work out. There's too many unknowns. But in statics, here's the rule. I don't know if you guys remember this, but in statics, you first try to do the whole free body diagram. And Braxton tried that and he couldn't get anywhere. But then Braxton says you break it into parts. Or he used the word sections, that's fine. But see, you break it into parts. Well, now the obvious way to break it would be to go from A to B and talk about that part there, or go from B to C and talk about that part there. Now, Braxton, did you try going from A to B and do that part? Did you try that one? I know what you did was you did BC, but did you try AB?
I have not tried AB.
It doesn't work. I mean, you can try it, but there's too many unknowns. But what Braxton did is he looked at this part, BC, And that opened up the whole problem. I don't know if you guys knew that, but that's what you're supposed to do. Do the whole free body diagram, and if you don't get anywhere, then you break it into parts. I know you've done that. It's just that maybe you need me to remind you. Okay, well here, let's break it into this part. We're looking at BC now. And I'll just draw BC by itself here. And this is going to bore Braxton because see, he already understands this. Now here's what you've got. You've got a force here of 12 kips. That's given. Whoops. 12 kips, that's given. You got an unknown force at C. And who knows what you got here, but you can't have any moments. That's a smooth pin. There's no moments, but you could have forces going up or down on, we don't know which way right now, but we'll figure it out. But see, we don't care about these forces because they go through B. They go through B. So what you do is you go sum of the moments about B is equal to a negative 12 kips times the 3 feet plus the force at C times the, well, it would be 9 feet equals 0. See, there's 9 feet from here to C. And then you solve that. 12 times 3 is 36. And then FC, it would have to be 4 kips, just like Braxton said it was. Hey, we made progress. We got 4 kips going up at F sub C. Interesting. Well, that must mean that if you got 12 kips going down and 4 kips going up, I drew that too long, didn't I? This one is the bigger one. 12 is bigger than 4. If that's 4 going up and 12 going down, well, what do you have to have it be? Well, you've got to have 8. There's got to be 8 going up. I'll just draw it here. This is fine. You have to have 8 kips. Where? It's messy. You have 8 kips going up here at B. There we go. Well, where is that 8 kips coming from? Since Braxton helped me on this, Braxton, where's that 8 kips coming from? Earth calling Braxton. It's not an external force. I don't see any external force of 8 kips going up on that.
Oh, is that your internal shear?
No, it's not. It's on the pin. It's not shear. See, shear is something that would occur inside the member, but it is 8 kips. But where is it coming from? That force has to come from someplace. Braxton's not sure, I don't think. Anybody have any ideas where that 8 kips? It's got to come from someplace. It's got to be there. Look, 8 plus 4, this is 4, right? 8 plus 4 is 12. So you know there's got to be 8 kips there on that pin at B. But where is it coming from? Anybody want to tell us? Just go ahead, tell us. Nobody's going to speak up. You guys are too shy. Let me pick on somebody here. I bet you guys know where that 8 kips is coming from. Let's pick on Alex. Alex, unmute and say hello, please, Alex.
Hello.
Alex, we know there has to be an 8 kip force acting on this pin going up at B. It's got to come from someplace. Where do you think it's coming from, Alex?
Actually, my guess was shear as well.
No, see, shear is something.
That's wrong.
No, shear isn't going to cut it, Alex. Shear is something that occurs. It could go up. Sure, absolutely. Shear can go up, but it's something that occurs on a surface. This is a force on a pin. It's not a shear force. Okay, well, I'll just tell you guys where it's coming from. It's coming from AB. See, AB is putting a force on BC. And guess what? BC is putting a force on AB. It's Newton's third law. I know you've heard of it. Newton's third law says for every action, there's an equal and opposite reaction. And that 8 kips is coming from the rest of the free body diagram. It's coming from that AB. Here, we'll draw it here in a little while, but let's go on and finish this because we've got to get these two things. Braxton got those for us. Let me make some room here. It's kind of like this. You're sitting in a chair, right? Well, you're putting a force on that chair equal to your weight. Well, guess what? The chair's putting a force on you in the opposite direction going up. You're putting a force on the chair going down. The chair's putting a force on you going up. It's a Newton's third law force. This member has a force on it going up caused by this other member, and this member here has a force on it going down caused by this member. Newton's third law. If you don't learn anything else today, you've learned that you have a force acting on you from the chair pushing up on you. Do you believe me? Okay, well, let's get these other forces. Now here, we made progress. We have 4 going up, 12 going down, and 18 going down. So we can figure what this FA is. I could write it out for you. Here, I'll write it out for you. The sum of the forces in the y direction is 0. And what you got is FA going up, 18 going down, 12 going down, 4 going up. It's equal to 0. So what's FA? It looks like 26. Did I do that right? Yeah. See, this here has to be 26 kips. And that's what Braxton, I think that's what Braxton said for me. Yeah, that's what he told me. He said it was 26 kips, and he was right. Now let's get this bending moment. Okay, now the way you get that is you take the moments about A, and you have that bending moment. This force here doesn't give you a moment, it goes through A, but this one does. It's a negative 18 kips times 4.5 feet minus the 12 kips times, well, that'd be 12 feet, wouldn't it? 12 feet plus your 4 kips that we figured out times, well, that'd be 18 feet, wouldn't it? Equals 0. Ta-da. And then you put all that in your calculator, and you get what I got and what Braxton got. What I got was 153 kip feet. But why don't you plug that in? I'm going to do it to make sure this is right. You plug that in and see if that works. Here goes. I'm double checking this now. Boy, Jove, when I plugged that in, I got 0. So now we know what this bending moment is. It's 153. I don't have much room there. I'll write it here. 153 kip feet. And what is that? Counterclockwise. So we've made a lot of progress. We've got all the red stuff figured out. See, that's 18 kips, 12 kips, 4 kips, 26 kips, 153 kip feet. And we know that moments are measured in kip feet, not kips. So maybe we've already been worthwhile this morning on that. Now let's move on. Any last comments or questions before we move on? Okay. Well, the next thing we got to do is the shear loading diagram. Okay, let's draw it. We're going to draw the shear loading diagram. And the bending moment loading diagram. Gee, I don't know if I got enough room here. Let me scoot that one up just a tad. Let's see if we have. See, we know what this is. It's 26 kips. 26 kips. I need to scoot that up where I'll have enough room for my bending moment loading diagram. See, we're going to plot our shear loading diagram, and then we're going to plot our bending moment loading diagram. Okay, now again, you guys can sit there and watch me do this stuff. But I've been doing this stuff for years, and some of this is new to you guys, or a little bit new. We've studied it. You were supposed to know how to do this when you walked in to my class. Wait a minute, we don't walk into classes anymore, do we? This crazy world of ours. I think what I'm going to do is I'm going to let you work on that for a minute. I'll give you 2 minutes. See if you can draw that shear loading diagram for me. We're going to do both. If you got time, work on the bending moment loading diagram. I'm going to shut up again. I'm going to give you guys a couple of minutes if you need it. See what you can do. I think you'll learn more trying to do that, and maybe discovering that you're a little bit rusty at that. Okay, I'll be quiet. Draw the shear loading diagram. I'll give you 2.5 minutes. How's that? I'll go see how my grandson is doing. And I'll be quiet and I'll let you work on that, and then we'll do it together. But his daddy's not coming up. Well, there's such a thing as food poisoning, right? Yeah. Well, I'll go say hi.
The nurse said he didn't have a fever, so
Yeah. But he's,
probably was trying to get rid of something.
but he can't go tomorrow.
Yep.
Dang, too bad. Well, tomorrow's Friday, right? Well, he'll just have a nice long weekend to get well.
Right.
Uga. Sorry you threw up. But you got to practice. That'll be okay. Really good. Well, I know I didn't give you enough time. Some of you are probably still struggling with that. But here, let me tell you this. You see that smooth pin right there? Smooth pins can't give you any moments. So if you come straight down here, you know that's going to have to cross the axis with 0 moment. Also, this roller, that roller doesn't give you any kind of moment. So there's going to be a 0 there too at that roller. Now on the shear diagram, the way you do diagrams, you take a left-hand section. So if you section this and just looked at it real close to the fixed connection, can you see that you've got to have a force going down? Well, it'd be 26 kips. So this would be 26 kips. And then it goes down because these are all pointing downward here. The resultant is 18, so it goes down 18. Now what's 26 minus 18? See, that right there is 26. 26 minus 18, I think it's 8. So see, this goes down to 8 right here. It just goes straight down. And then it stays right there at 8 for a while. Not mosh. And then it takes a 12 kip drop. If you're at 8 kips and you drop 12, that puts you down to -4. So that's right here. Straight down. And we're done. Ta-da! We are done. We got -4 kips. There's the shear loading diagram. We could spend more time on that, but we've done that before. Now the bending moment loading diagram. Again, to find it, you do a left-hand section. You do a left-hand section. Can you see that you're going to have a bending moment clockwise? See, that's counterclockwise. That's an external bending moment caused by the fixed connection, but right close to the fixed connection inside your piece, internally, you're going to have an internal clockwise bending moment, which is negative 153. Well, that's way the heck down here someplace. Does that show up? Yeah, that shows up. Negative 153 kip feet. And then what happens is, see this trapezoid right here? You can get the area of that trapezoid, and that's how much it's going to go up. Trapezoid area, what you do is you take 26 plus 8. Let me write it over here. 26 plus 8 divided by 2 and multiply by the base, which is 9 feet. That's how you take the area of a trapezoid. You take the two heights, divide by 2, multiply by 9. And I don't know what that is, but my calculator does. Let's see. 26 plus 8 divided by 2 times 9. I'm getting 81. Something bad happened. That's not right. See, what I'm trying to tell you is that the change in your bending moment should equal the integral of your shear force. And I just took the area. And this is 26 kips, isn't it? Yeah, that's right. 26 plus 8 divided by 2 times 9. No. I'm getting 153 this time. Is that what you guys get? Let me do that again. 26 plus 8 divided by 2 times 9. Yeah. We're going to increase by 150. Well, that brings us up to 0. And the thing is, the slope here is going to be bigger and the slope gets a little smaller. It goes like this. See, the other equation goes like this. The shear is equal to the slope of the bending moment. The slope here is pretty big. 26 is pretty big. The slope here is smaller. It's only 8. So that's a smaller slope. Probably even smaller than that. It probably goes like that, maybe. Something like that. There we go. And then what happens? Well, it continues up by the area of this. That's 8 times 3, right? 3 foot here. The height is 8 kips. 8 times 3 is 24. It's a constant slope. That puts you to 24 right about here. Straight line. And this value is 24 kip feet. And then you go down, according to this area here, this is 4 times 6, that's 20, you go down 24. But see, it's negative, so you drop down gradually. Bingo. We have just drawn the bending moment loading diagram. That's what it looks like. There's your shear loading diagram. There's no line right there. And there is your bending moment loading diagram. A little bit messy, but not too bad. Okay, good. Now what? Well, they wanted to know the maximum shear stress, I think. Let me read this again. If you just woke up from a daydream, we're doing problem 688. And they want the absolute maximum bending stress. Okay, well, the way you get that, need some room here. They want the bending stress. We don't need any of this stuff. Was there any question from anybody about those diagrams? Well, I guess not. All right, let's get the bending stress. Here we go. We're going to use the flexure formula. And if you want the maximum bending stress, it's going to be, well, you'd want the maximum bending moment. Well, that'd be the 153. Never mind the minus sign. All that does is tell you, it tells you whether you have compression or tension, doesn't it? And it seems to me that you'll have tension on the top because this thing's trying to bend down, I think. Yeah, and you'll have compression on the bottom, but we just want the maximum. It's going to occur here. It's going to occur where you have your maximum bending moment. Does that make sense? Does it make sense that the maximum stress will occur where you have the maximum bending moment? Makes sense to me. It also will occur where this Y is maximum. Remember, we have a, I think it's 4, is it 4 by 12? Is that what it is? 4 inches by 12 inches, I forget. Yeah, that's what it is. And what you want here for your maximum Y, you'd want to have that maximum Y, that'd be 6 inches, wouldn't it? 6 inches. Okay. And then you divide by I. Dang, I erased my I. But we had it on the board. It was 576. We had it up there early. But I'll go back through it if you need me to. Inches to the 4th. All right, do that and tell me what you get. I'm going to do it. You do it. And tell me what you get. Go for it. I'll be quiet. You got a minute? I want you to find the maximum normal stress, which will occur right here at the fixed connection. And I think it's going to be a tension on the top of the beam. Do it. See what you get. Are there any brave souls out there that want to tell us what they got for the maximum normal stress? It would be tensile on top of the beam and compressive on the bottom. Go ahead, somebody.
I got 19.125 kip
That's
per inch squared.
That's what I got. I got 19. Now, who am I talking to?
Jackson.
Jackson. Jackson, I need the units. Now, what are the units that we need here, Jackson?
Kip per inches squared.
That is correct. Good going. Now Jackson said kips per inches squared, and he's absolutely right. Or you could write it like this. You could just say KSI. That's the same thing. But see, I thought I was going to fool you guys. To get Jackson's answer, you have to multiply by 12 inches over a foot. Didn't you, Jackson? Didn't you?
Yeah,
Proud of you.
that's right.
Proud of you. Because see, if you don't do that, you're going to get the wrong answer. You have to do that to get rid of those stinking feet there. See there? And if you'll do that, you'll get the answer. Now let's see how we did. All right, go to the back of the book. This is problem 688. Go back here, find 688. And let's see what the book says. 688. They say, the bums, they don't do even numbers. Well, I looked this up in I got an answer book that has even numbers, and they said 19.125 KSI, so we're happy, we got it. They don't give you the answers to everything in the back of the book. Now, is there anybody else that has a comment or question on that? Well, I didn't hear anything. Let me go back to something we were talking about earlier. If you're happy, I need the room here. If you're happy, I'm going to erase this. Okay. Now, earlier we were talking about this BC thing. See, here's BC. And we know there's a force going up here of 4 kips. And there's a force here of 12 kips. And then there's didn't we decide there has to be a force here of 8 kips? Now let's draw the forces on the other half of our free body diagram. We have that distributed load, which gives you, what did we say it was? 18 kips. And a bending moment of, it was 153 kip feet. And FA, what did we say that was? Oh, gee, it was 26 kips, wasn't it? It was 26 kips. And what did we say about this pin B here? We said something about this pin B. We said if there's 8 kips going up on this one, caused by AB, there must be 8 kips going down. Whoops, need red for that. There must be 8 kips going down. Now let's check that and see if that works. Does 18 and 8 add up to 26? Well, yeah, that works pretty good. Let's look at the moments here. The sum of the moments about point A, or you could do point B for that matter. Here, let's do point B. The sum of the moments about point B. This is called checking your work, guys. They don't have answers in the back, but that's okay. We don't need their stinking answers. Okay, sum of the moments about B is going to be 18 times 4.5 minus 26 times 9 plus 153 equals. Now, if that equals 0, we did it right. Get your calculators there and go 18 times 4.5. How come it's positive? Because it's counterclockwise. That's how come. See, this distance is 4.5 feet. That's a counterclockwise moment, and so it's positive. Now this is a negative. See that 26 kips times 9 feet? It's negative. Plus 153, that's positive. Okay. I'm adding this up now. 26 times 9 plus 153. Boy, Jove, I get 0. The sum of the moments is 0. There's an 8 kip force acting at B on this half of the free body diagram. Where does that 8 kips come from? Let me ask one of my excellent students here. Ben Seaman, unmute and say hello, Ben Seaman.
Good morning.
Yeah. Hey, Ben, you see that 8 kips that's acting down at that pin on B? It's not an external force. There is no external 8 kips. Ben, where does that 8 kips come from?
You have to have the 8 kips there to have equilibrium in the section.
Yeah. Now, where does it come from, though? Forces have to have a source. Like if that bully at school, when you were in grade school, punched you in the nose, that punch had a source. The bully. Where did this 8 kips come from? Ben.
I am not too sure.
It came from BC. See, BC acts on AB, and AB acts on BC. Newton's third law. Forces have to have a source. They don't just appear out of thin air. Okay, well, we have 6 minutes left. And I want to talk to you about this beam. Unless there's another question there. I'm going to erase some stuff. I need some room. All right. I'm going to talk to you about this beam here for a minute. Now that beam, I think, was a 4x12. That's pretty good, hefty wooden beam. I hate to go and buy one of those at the lumber yard. Is that what it was, 4x12? Yeah, that's what it was. Did I do that to scale? Yeah, pretty close. I might have made it a little too tall. But it's It's about right. Now let's suppose this is made out of a material who has a yield strength. We'll just make something up. Suppose it had a yield strength of, we'll say it's 250 megapascal. That happens to be the yield strength for structural steel. My question to you is, what is the, they have a name for this. They call this the maximum elastic moment. I wonder if you remember how to do that. Let me shut up for just a minute. See, what that is it's the moment that you apply to this beam. Now, this is a beam here. Pretty big beam. If you go to the lumber yard and buy one of those, it's going to cost you some money. That's not a 2x4, is it? And even they aren't cheap anymore. But to find the maximum elastic moment, we've studied that. Gee, we don't have time for you to have time to do it. Here's how you do it, and I'll write the equation and you can find it for me. We know the flexure formula. We've memorized it. And see, if you put in your yield strength, then this will give you the maximum elastic moment, but you have to take the maximum distance, which would be 6 inches. Do you understand? From the center. They call that C in this book. They said C would be 6 inches. And then you divide by your moment of inertia, which I wrote down someplace. Let's see if I still have it here. We did that earlier. It was 576 inches to the 4th. Okay, we've got this. Look, it's 250 mega. Wait a minute, Auga. We can't mix metric with English, senor. That is not permitted. We've got to find the English version. Let me look it up. It's, well, I should have known this. I should have known this. The yield strength in English for structural steel is 36 KSI. Can you find it? It's in the back of the book, back flap. It's right here where my finger's wiggling, in the back flap of your book. Okay. Oh gee, we only have 2 minutes left. So we have that, and we can solve for your maximum elastic moment. Now it'll be in inch pounds. Go ahead and do that. I'm going to do it. I want you to do it. I want you to solve for the maximum elastic bending moment. Go for it. Well, I got an answer. I got 3, 4, 5, 6. 3, 4, 5, 6 kip inches. How about you? 3, 4, 5.
Yeah.
3,456 kip inches. Now, if you wanted kip feet, you could get it. Just divide by 12. Divide by 12. And what you'll get is 288 kip feet. 288 kip feet. Now, are we in any danger of yielding on our problem? Well, the maximum, remember the maximum bending moment was 153 kip feet, and you don't reach yielding till you get to 288 kip feet. So we're nowhere near, well, we're near, I guess, but close to halfway, a little more than halfway, but we're not yielding at all. So now we found the maximum. Now, what would be fun? Oh, gee, we're out of time. I was going to do the fully plastic bending moment, but we are out of time. Here's your last chance to say anything before I push this red button. Speak up now, or else I will see you when Tuesday at 9:30. Yeah, I'll see you Tuesday at 9:30. Last comment, anybody? Okay, well, bye-bye, students. See you next time. See you Tuesday at 9:30. Goodbye.
Have a good day, Mr. Griffin.
You too.
Bye.
See you then. Bye-bye.